We've spent a lot of time talking about photovoltaic technology, how the cells are made, how they work. Now it's time to look more at the finished product, a complete module, and talk about how do we predict the electrical output of a module in a given installation. That's the kind of information that we're going to need to be able to do system sizing. We need to go from the instantaneous electrical characteristics of our cells and our modules and make a translation to be able to predict amp hours or watt hours or energy out of a module in a typical day in a particular location. With that kind of information, then we can match up the number of modules to the size of the electrical load, and we'll be able to size our array. So what we're going to do in this segment is take some time to look at how we characterize the electrical output of a cell or a module, and how we sort of animate that prediction or spread that prediction over an entire day to accumulate energy out of a module. We have to begin with one of the most fundamental characteristics of a solar cell or solar module, and that's the output curve, what we often call the current voltage curve or the IV curve. This is like a signature. It's a fundamental measure of the instantaneous output that you might get from a single cell or a collection of cells together making up a module, or a collection of modules together to make an array. So let's take a minute to look at what we mean by an IV curve, what it looks like, and what are some of the characteristic values that are important. The shape of a module IV curve is always something like this. On the axes of what we're measuring, we have current measured vertically and voltage measured horizontally. The black line indicates the output of a cell or a module at different voltages and currents. Notice the general shape, the curve is fairly flat, in other words, fairly constant in current at low voltages, until we get to a point where the voltage increases, yeah, but the current starts to drop off. And then finally, the current plummets down to a value of 0. Let's look at some characteristic points on this curve, because they're always indicated in all manufacturers' literature, and we use them in our system sizing calculation. If we begin in the upper left-hand corner, that point corresponds to what we call the short circuit current, ISC. What do we mean by that? We mean that effectively you've taken a module and taken the plus and minus wires and put them together. You've shorted the module. Now you can't do that with a battery or a generator. It's dangerous. There are extremely high currents that flow, and the device is actually damaged or could blow up. With a photovoltaic module, it's fundamentally current limited. It's safe. It never produces more current than it can produce. It never runs away. So there's an upper limit to the amount of current that a module or a cell or a module together can produce. At the other extreme of the curve, the far right-hand corner, we have a value that we call the open circuit voltage, or VOC. What do we mean by that? That would be the condition of a module just as I have it here. The plus and minus connections of the module are not connected. The module might be receiving sunlight, but there's no current flow. It's at open circuit. That's the point of maximum voltage, but there's 0 current flow. These two extremes of short circuit current and open circuit voltage are points of no power. At short circuit current, we have maximum current, but 0 volts. At open circuit voltage, we have maximum voltage, but 0 current. Both of those indicate 0 power. In between a point of 0 and 0, there's some place where there's a maximum. And the point of maximum current occurs somewhere out here on what we call the knee, the point where the curve really starts to bend. The point where we get maximum voltage and current together at the same time is indicated by 2 points, a maximum power current, IMP, and a maximum power voltage, VMP. The product of voltage times current gives power, and that point is the point of maximum power for the entire module. For example, I could take a 12-volt module and operate it at 6 volts. There'd be no harm. but the amount of power coming out of the module wouldn't be the same, wouldn't be the maximum that I could possibly extract. We can look at IV curves for different types of modules, modules made with different sizes of cells, different numbers of cells, and we can characterize each one of those modules with its own sort of signature curve that represents the potential output from that particular module design. Let's look at the family of curves that we can create from our M series of modules, the power modules that we call the M55, M75, M65, and so on. Again, we're looking at IV curves with current along the vertical axis and voltage along the horizontal axis. Let's look at the farthest reaching curve. That's the M55. That's a module made up of 36 solar cells connected together, plus to minus, plus to minus. The current that we get from the module, the short circuit current, is about 3.4 amps. The open circuit voltage is around 22 volts. The M75 module is the next curve. It's made of the same size of cell, the same type of cell, but there's only 33. So with 3 less cells, we get a little less voltage. Each cell, remember, contributes about a half a volt. The M65 is made with 30 cells. So there again, it's got 3 less cells, 1.5 less volts. All of those modules are what we call power modules. They're made with full-size cells. We can actually take the cells that make up the standard modules and cut them in half or quarter to give us less current. We do that on the M20. That's the next curve down. There, we've taken the standard cell and we've cut it in half. By reducing the area by half, when sunlight shines on the cell, half as many photons strike it, so half as many electrons come out. We get half as much current. So the size of the cell will be proportional to the current. In this case, the M20 is made with 30 cells, so it has the same voltage as that M65 module that also had 30 cells. We have a couple of other modules to look at. We can look at an M10 or an M5. Those, again, are modules made with cells cut even smaller to give less current. So the family of curves we have here represents different sizes of cells and different numbers of cells connected together in series. We've recently created a new type of module and a new type of cell, a larger, more rounded cell that is more efficient for us to make, which we call the Power Max cell. We put those together into modules which we call the ProCharger line. We can look at those IV curves as well. There, again, we have current and voltage characteristics. The PC4 is the largest power output module, rated at 75 watts. There, it's got a short circuit current of almost 5 amps because of a larger cell, and open circuit voltage of about 22 volts because of 36 cells connected together in series. Then the PC2 and the PC1 are simply modules using the same kind of cell, but the cell is cut in half or in quarters. The point is that we can, from individual cells, build up modules of different voltages, different currents, and therefore different powers. You can refer in your manual to tables that describe the different powers and different characteristics of your module. When we characterize the module output using the IV curve, that's one description of the instantaneous output of a module. There's some other measures that we need to know, specifically dealing with efficiency. It's real important to understand the definition of efficiency and how it applies to solar modules, because all manufacturers and all sorts of folks involved in the industry refer to module or cell efficiency all the time. I want to make sure that you're clear on what it means. There's really two kinds of efficiency measurements that are made. One is called active area efficiency, and the other is called total area efficiency. What's the difference? First of all, before I go into that, let's make sure we understand about efficiency. Efficiency in general is a measure of what I get out compared to what I put in. In the case of solar cells, it's a measure of electrical power out versus solar power in, comparing the the watts that I generate given so many watts of solar energy coming in. If I talk about active area efficiency, what do I mean? In a cell, and even in a module, there's lots of what we call dead area. There's printed areas that are covered up, so light, photon particles, can never get into the cell. Those are dead. They don't actively produce current. In a module, that would be the spaces between the cells, the size of the frame around the module, and so on. The interconnect ribbons that cover the cells, those are dead areas. On the cell, there's the room for the interconnect wires. There's the thin white lines that are the grid lines that collect electrons from the cell. All of these are inactive areas. So if we want to measure the active area efficiency, we subtract away any areas that are being covered up to make an actual cell, and then we measure its output. The efficiency is calculated by measuring the output of a device and divide that by the density of light that's shining and multiply that times the active area, only, in this case, the blue area, only the areas that are actively producing output. This measure of active area efficiency is what's typically quoted by research organizations. Anybody that's announcing a new cell technology efficiency, they'll say breakthrough, such and such efficiency is being announced. What they're talking about is typically the active area efficiency, just the efficiency of the physics itself. That's what scientists are concerned about, and laboratories will compare one to another. That's a value. But we have to go one step further. We need power in the field. So what we need to do is connect cells together, interconnect them with wires, space them out. We need to introduce some dead area. So when we finally create a finished module, we've got a device that has cells that are separated in between spaces that aren't producing electricity, ribbons that are covering up the cells, frames that are taking up space, and so on. This becomes a real device that we use in the field. What we really care about is total area efficiency. Take into account all the bloody space that's being used, even the stuff that's kind of dead. Shine light on the module and measure the electrical output, and divide that output by the total area of the finished module. That's what we call total area efficiency. That number is usually less, because in active area efficiency, you're only looking at the particular part of the cell that's working. In total area efficiency, you're looking at the total module, and there's more area taken up by dead space. So be careful and notice the differences between those two if you hear any announcements. Now, one thing that we need to look at is not the instantaneous measure of a module, but how it's affected by the environment. The three critical factors that determine the potential output of a module are the light level, the cell temperature, and the spectrum of light that's shining on the module. So let's take a look at each one of those factors and see how it influences the output of a module. Let's begin by talking about the effect of light level. We can use a more precise term for that, for light intensity, and we call that irradiance. Don't be confused with insolation. These are two terms that often come together. Insolation is a measure of solar energy over time, like over a day. Irradiance is a measure of instantaneous solar power shining on a module. What we can notice is that if we measure the output of a module under different levels of irradiance, we'll notice that the curve has sort of different heights. In other words, if we start at a low light level and then increase the light level available to us, the current output will increase. That makes a lot of sense. The more photons that are shining on the cells, the more electrons are being knocked loose, the more current that flows. It turns out that the short circuit current measure from a module is directly proportional to the solar irradiance. Brightness of the light and the solar current go together. Because output depends so much on light level, we have to choose a standard. We have to somehow standardize so that manufacturers compare apples to apples. The standard level that's chosen is 1,000 watts per square meter. We often call that 1 sun. It sounds pretty arbitrary, but it's not. It's actually a measured value at the equator, at sea level, under certain conditions of clarity of sky, we measure 1,000 watts per square meter. Outside of our atmosphere, we can actually measure 1,350 or so watts per square meter. We lose about 350 going through the atmosphere. We're left with about 1,000 at noon on the Earth's surface. That would be a value that we would use as a standard measure, 1,000 watts per square meter. Can you measure more? Yes. Typically you measure less. Clouds come by, there might be atmospheric moisture, smog, dust, cloudy days. That's going to lower your light level, of course. But there are conditions under which you can measure light levels greater than 1,000. What might those be? You can actually have light reflecting. You can have reflection off of bright surfaces, buildings, white sand in front of the modules, white snow. You can also have what's called edge of cloud effect, where you have a clear blue sky day and white billowy clouds. The light not only comes directly from the sun, but bounces off of the white clouds, and you can get 1,100, 1,200, 1,250 watts per square meter. So it is possible to measure more. Typically, you measure less, and the standard that's chosen is 1,000 watts per square meter. Now, the other factor that's critical in predicting module output is temperature. And by that, I'm referring to cell temperature, not general air temperature. The effect of cell temperature on the module is kind of interesting. As we increase the temperature of the module and the cells in the module, we lose voltage potential. If you look at the curve carefully, you'll notice that way over here at short circuit current, the current value actually goes up a little bit. But the major effect is that we lose voltage potential, and it's a linear effect. The hotter the module gets, the more voltage we lose. Because output is dependent on temperature, we have to choose a standard. And the standard that's been chosen amongst all manufacturers is the standard temperature that's used for most measurements, 25 degrees centigrade. That's about 77 degrees Fahrenheit. Will your temperature vary? Yes, most assuredly. Typically, your temperature is always higher. Put the modules out in the sun, they're going to start cooking. But the 25 degree level is at least chosen so that manufacturers can compare apples to apples, so that we can at least compare our IV curves under standard conditions. In terms of the amount of power that's lost, a typical factor that we use is roughly about 0.5% loss per degree. 0.5% of your power is lost for every degree centigrade that those cells heat up. We have to know about this when we predict module output. You say, my God, you have a 53-watt module prediction here at 25 degrees. Now I'm going to take this module, put it outdoors, it's going to get hot. I'm not going to have as much power. I'm not going to be able to run my loads. That concern is handled because in our sizing calculations, we know how to predict how much power is lost. We have weather data that allows us to predict what the temperature profile is going to be day by day. So we can predict the amount of voltage loss, and we size our systems to take that into account. There's a third environmental factor that we've got to take into account to predict and understand instantaneous module output, and that's the light spectrum, the light distribution, the amounts of blues, greens, and reds that's shining in that light irradiance that we talked about. That's because different wavelengths of light, different types of photons, will affect the cell differently. A certain amount of blue light shining on a module will not give the same electrical output as a certain amount of red light. So we've got to make sure that we know very well the spectrum of light that we use in our solar simulators so that we can compare to other simulators around the world. There's not much that you can do about predicting or controlling the solar spectrum. So it's not something that we use in our sizing calculations. But it is a factor I want you to know about because it's in all the literature, so you better understand. The factor that we're dealing with is the spectrum of light. But an interesting way that we characterize that is by the thickness of atmosphere that the light has to go through. Our atmosphere acts like a filter, taking out certain amounts of blues and greens and reds. The industry has standardized on a situation predicting roughly around 10 o'clock, 10:30, where the light is shining through roughly 1.5 thicknesses of atmosphere. We characterize those conditions and call it air mass 1.5. Given that thickness of atmosphere, we get a certain type of solar spectrum, certain amounts of blues, greens, and reds. And given that spectrum that we can simulate in electronic simulators in factories, we can predict module output and compare that to any other simulator in the world. Remember, we have a spectral response curve from our solar modules, our solar cells. Different types of technology, thin film silicon, copper and diselenide, single crystal silicon, these will all respond slightly differently to the same light. So what we need to do is at least hold the kind of light solid and constant. So in literature that you read about modules, you'll often see module output characterized for an M55, let's say, is 53 watts under these conditions. Light irradiance of 1,000 watts per square meter, cell temperature, not air temperature, cell temperature of 25 degrees C, and air mass 1.5. These would be the standard characteristics that would be used to measure cells and modules around the world. We've looked at a cell and a module. We've talked about the curves. Let me take a minute to show you how we can actually sort of add up cells to make a module, both physically in a module and graphically in curves. The output curve for a single cell has the same shape as we've looked at already, fairly flat current-wise and then suddenly dropping off down to zero current. If we connect cells together in series, in other words, connecting minus to plus, we're adding up voltage. The voltage gained in one cell is added to the voltage gained in the next. We can graphically show our cells being drawn together in series, and we can actually show the IV curves of two cells added together to give a composite curve for the combination of the two. And it's just graphically the sum of the two. So notice that when we add cells together voltage-wise, or in series, we add up voltage and we stretch out the curve. We show that the cells combination produces the same current, but double the voltage. Now, we can also connect cells together in parallel, where we connect plus to plus and minus to minus. In that case, what we would be doing is physically connecting, let's say, the fronts of some cells together and the backs of those same cells together. What we would be doing is then adding the current from one cell to the current from another cell. This would be a way to gain more current than you get from one cell. Graphically, we're adding up current, so we simply add the graphs current-wise. The graphs grow up. We have same voltage potential because we have the cells connected in parallel, but we add up the current that we could get from cells connected together. So what we can do is physically connect cells together into modules, and then graphically we can also predict the result of that many cells graphically and mathematically, as we show here. An individual IV curve for a cell might have a short circuit current of about 3.4 amps, an open circuit voltage of about 0.6 volts. If we have 36 of those cells added together, we have 36 IV curves added up for a final voltage of about 21 or 22 volts. So the IV curve of a module is just the sum of the IV curves of the individual cells. And the IV curve of an array of modules is just the sum of the IV curves of the modules added together. For example, we could have an array made up of a string of 4 modules in series. If these are each 12-volt modules, that would be 12 times 4, or 48 volts nominal. And we could have multiple strings connected in parallel. So we connect the plus of one string to the plus of another, and the minus of one string to the minus of another. That would be adding current. So in terms of the IV curves, what we would do is we'd add up 4 module curves in series to get an open circuit voltage of more than 80 volts, and then take 2 of those curves and put them on top of each other to add up current. So instead of having only about 3 amps, we'd have 6 or almost 7 amps of current. The IV curve of an array is simply the graphical sum of the IV curves of the different modules that make it up. And the IV curve of a module is just the sum of the individual cell curves that make it up. What we want to do is go from all the discussion we've had so far, talking about instantaneous module output, module IV curves, watts. We want to move to a discussion about energy, watt hours, the output of a module over time, like over a day. So what we want to do is build on the knowledge we've got so far about predicting module output by looking at the IV curves, and understand how a module interacts with the environment and the load. That's the fourth element that we need in order to fully predict module output in a particular place under particular conditions. We've talked about light level, cell temperature, and solar spectrum as determining the instantaneous module potential output, the IV curve. We need to add in a fourth element, and that's the load. And the load is going to operate the module at a certain point on the IV curve. And that's going to give us our actual current and voltage under a particular situation. And then what we do is we look at how that load interacts with our module over a day, how the environment interacts with the module over a day, and we can predict module output under real situations. So let's take some time to look at the different types of, or the different classes of loads that can interact with modules. And there's basically three types of loads. There's a maximum power tracking type of load, an electronic interaction with the module that operates at its maximum power point all the time. The more common type of load, which is just hooking the modules up to a battery and letting the battery operate the module. And the third type would be connecting the modules directly to a water pump, a motor, a DC motor of some type. Those three different types of loads are going to operate the module in three different ways. So let's take a look at how those curves might change from an individual snapshot into a motion picture, sort of the IV curve changing over time. One of the first things that we have to look at is the dynamic effect of cell temperature under changing conditions in the day. We actually have a measured curve that we use in our computer predictions to predict the temperature rise. In other words, the difference between air temperature and cell temperature based on irradiance, the intensity of light falling on the module at any one moment. The relationship is linear, and it's pretty straightforward. The more light, the hotter the cell. And that makes a lot of sense. What's interesting is that we're looking at not cell temperature, but temperature rise above air temperature. We can read off of a graph like this a certain irradiance level at a particular moment, read up on the curve and read across to find the temperature rise above air temperature that the cell has equilibrated to. Given a profile of temperature, of air temperature profile, and given a profile of light irradiance, moment by moment, we can predict at, let's say, 11 o'clock in June for a particular location, what the light level is going to be and what the air temperature is going to be. And we can put these two together with the help of a graph like this and predict what the cell temperature is going to be. Now, knowing the cell temperature and the light level, we can predict an IV curve. And knowing the IV curve and the voltage of the load, we can see where the load operates the module. Let's put that together for a particular type of load, the maximum power tracking type of load. This might be used in utility interconnected inverters, the type that don't use batteries and sell power directly to the utility during daylight. Or they might be driven by electronic max power tracking boxes, devices, that make a good match between modules and motors. we can look at a sequence of IV curves during a day and look at the curves at early in the morning, let's say 8 o'clock, then later at noon, and later still at 3 o'clock in the afternoon. And notice that we've marked out the maximum power point, the point on the IV curve that gives us maximum power at that moment from that module. That would be the points A, B, and C. If we plotted out A, B, and C and all the other points in between over time, we get the second graph, where we're looking at power on the vertical axis and time of day in the horizontal axis. And you can see the characteristic curve of output from a fixed module over time. If we add up all of those watt values times moments of time, we end up with the area under the curve predicting watt hours of energy. So we've gone from an instantaneous snapshot of output from a module, which is characterized by the IV curve. That's measured in watts. And we've animated that over time. We've looked at that power output distributed over a day, and we end up with a prediction of watt hours, or energy. That's what we need to know to do our system sizing predictions. Because if your load in a particular day needs so many watt hours of energy, and your module produces so many watt hours of energy, you simply divide the two, and it tells you how many modules you need. The second kind of general sort of load that we want to talk about is batteries. That's probably the most common. Max power tracking is important, but that market share is small. The most typical type of load that we connect modules to is some sort of battery. It could be lead acid or NiCad. That doesn't matter at this point. The point is that a battery is a huge, stable source of electromotive force, and it has a voltage, and it stays there. Now, as it's charged up, that voltage slightly rises, and as the battery is discharged, that voltage slightly drops. But the point is that the voltage of the battery will dictate the voltage of the module, not the other way around. So if we look at a scenario of different IV curves during a day connected to a battery, we see something like this. Early in the morning, we can guess that the load was used during the evening. The batteries were discharged during the night, some. So we start at a relatively low battery voltage. And the IV curve is low, let's say at 8 o'clock in the morning. We see that the battery voltage, take that line straight up, and that predicts the operating point on the curve, and that predicts the operating current of the module at that time with that load. Notice that it's a little different from that point A. That point A was that maximum possible power we could get from the module, and what we're getting is a little less. During the day, then, current flows into the battery gets charged, its voltage rises slightly. So around noontime, we have a slightly higher voltage, and the IV curve is changed. Notice that the matchup of battery voltage to the max power point, that B point, is real close. That's no accident. We put in the right number of cells so that we would have the right kind of voltage, given typical hot days, to match up to a 12-volt battery. So that matching up is no accident at all. Then later in the afternoon, the battery continues to be charged up, the voltage continues to rise a little bit, but now the light's going down, the IV curve is going down. Notice that the voltage of the module is starting to move out a little bit more. It's getting cooler, colder temperature, higher voltage. So what we now do is we look at the curve where we compare watts of power versus time of day. And we notice that we get a curve that's slightly different from the maximum possible power curve that we could have gotten. A slight deviation because that battery operated the module slightly away from its maximum power point. Not too bad. Sometimes people say introduce a maximum power tracking device to get that matchup even more perfect. We'll talk about max power tracking devices in another section and compare the pros and cons of that. But typically, in order to have a cost-effective system, we simply put modules together with batteries. And what we're looking at here is the fact that the battery operates the module in this fashion. And this is the way we predict the amount of output from that module into that battery. And finally, let's take a look at the third class or third type of load that we might have connected to a module, and that would be a DC motor. Again, it's the motor that's going to operate the module. So let's look at how this interaction might happen. We can look at a load curve for a typical DC motor. We've drawn one here. That's the upward slanting curve. It's a lot like a resistive line because a motor is just a bunch of wire, just a bunch of resistance. If we match up the load curve to the IV curves over time, we begin to see how the pump or the motor operates the module. Early in the morning, we see a curve at 8 o'clock, and we see that the pump curve intersects the module curve at around a little more than 6, 7 volts or so. The maximum power operating point was that point at A. We could get a lot more power from the module, but the motor doesn't operate the module at A. It operates it way back. That's just what we get. That's the inherent inefficiency of directly connecting modules to motors. Notice what happens though later in the day around noon. The module curve has risen up, we have more light, and the motor curve now is operating the module at around B, at around the maximum power point of the module. That's perfect. That's just fine. That was the design of this system. In the peak of the day, the modules and the motor operate together quite well. Then towards the afternoon, the IV curve starts to go back down again because the sun is setting. And again, we move away from what could have been our maximum power point, C. We move to a point more around 10 volts or so at around 3 in the afternoon or so. The point is that the motor is operating the module in a slightly inefficient way. But remember what I said in another segment where we talked about trade-offs in system design. We talked about having to make a trade-off between efficiency and simplicity and reliability. This is exactly an example of what we're talking about. You could add in more components to make this matchup more efficient, but you'd be adding in cost and complexity, and thereby somewhat reducing your simplicity and reliability. The trade-off is up to you. The question is, how important is efficiency? How important is simplicity and reliability? They're both important, so you've got to somehow make a trade-off. Later on in other segments, we'll look at a device called a maximum power tracker. In the case of water pumping, it becomes quite a valuable tool and can make this match up better. But it's often common to have modules directly connected to DC motors doing water pumping. Another example might be modules connected to a ceiling fan to give ventilation. It's not a critical load, and this would be the characterization of how the modules and the motors work together. So in summary, what we've looked at is taking a module, shining light on it, and getting an instantaneous output characteristic curve, the IV curve. This gives us an instantaneous snapshot of the potential output of the module. What influences this potential output? It's really 3 environmental factors and a final factor, the load. The 3 environmental factors were light level, or irradiance, cell temperature, and spectrum of light. Given those environmental factors, we get a rigid, fixed, predictable potential output from the module. What actually determines the final output from the module is the 4th factor, the load. And we talked about 3 different types of load classes: maximum power tracking devices, batteries, your most common load, and directly connected to DC motors. And we've seen that knowing the characteristics of the load and the characteristics of the module, we can predict over time the output of the module into that load. What we need to do in order to do our system sizing calculations is first estimate our loads. We might have DC loads, You might have AC loads. We need to go through a process of mathematically adding up what the various lighting, motor, appliance, device loads might be in a typical day. Then later, we'll be able to predict how many modules and how many batteries we need to safely operate those systems. So in this segment, let's take some time to look at the methods we'd follow to calculate the daily load demand from our DC and AC loads. And also, before we're done, we'll want to pay some attention to efficiency issues, because you don't just want to mathematically add up some loads without looking carefully at them and saying, whoa, these numbers are too high. Is there any way that I could use a more efficient load or change the type of device I use to get by with less energy demand? Because that's going to mean fewer modules and fewer batteries and lower cost overall. So let's begin by talking about the basic and relatively simple steps involved in adding up your DC and your AC load demand. We want to look at a typical 24-hour period, day and night. Let's look at DC loads and then AC loads. If we're adding up DC loads, let's say we have DC lighting or some DC appliances, you want to look at the current that each load might require in amps and multiply that times the hours of operation in 24 hours. That would be your amp hour demand. For AC loads, it's slightly different. We want to add up the watt hours that are used. So we look at the power that's required by each load in watts, and we multiply that by the hours of operation in 24 hours to give the watt-hour AC load demand. Once we have the AC load demand estimated, we will then choose an inverter that supplies AC power and be able to operate both AC and DC loads if we need to. If we're adding up loads, either DC or AC, a real important thing to consider is that loads are variable. They might be changing. They won't be constant all the time. That seems pretty obvious. But in terms of our calculation steps, you want to be as careful as you can be. You want to be as accurate as you can be about the actual energy demand. If a load isn't on 24 hours a day, don't multiply by 24 hours. Multiply only by the hours that it's actually operating. So one way that we can visualize this load profile or this variable load would be to take a look at, let's say, a variable load like maybe a telecom repeater. This could apply to other types of loads as well. There might be a specific load demand level for a telecom repeater that might be 10 amps. But that wouldn't be 24 hours a day. It might only be a certain fraction of the day, maybe a few minutes in the day. We also need to look at any quiescent current or standby current, where the load might be simply kept warm or kept in receive mode or kept ready to operate. That current level or that power level might be quite different. So what we need to do is not only be concerned about the peak current of any load, but the hours of operation during a typical 24-hour period, and add up the peak current or the operating current times its time, and add that to the quiescent current or the standby currents that might be there, and those times. And the quiescent currents can be significant, so be careful that you include them as well. Let's walk through the simple steps involved in actually mathematically adding up our DC and AC load demands. We've created for you some simple forms. You can modify them if you want, of course, but we give them to you as a guideline to get started. First one we'll look at is DC load calculations. Here you want to list out every DC load that might be operating, the current draw that it might draw, how many amps, multiply that by the number of hours in 24 hours, in a typical day, that it might be operating. And multiply that out, you get amp hours per day per load. At the end of the column, you'd add up all those amp hours per day, and you'd end up with a total amount of amp hours for your DC loads. Different loads might be different currents, might be different hours. Just make sure that you look at each and every load that might be operating. For AC loads, again, we list out each load that might be operating, but instead of looking at current demand, we look at power. We look at watts. So indicate the watts that might be drawn, the hours per day within 24 hours that that load might be on, multiply each one of those across to get watt hours per day. And then you add that up, that gives you the subtotal of watt hours per day for AC loads. When we're dealing with adding up AC loads, we have to consider choosing an inverter as a part of the sizing process. In your first phase of your calculation, you've added up watt hours per load and subtotaled that up. Now you need to stop and determine an inverter that's going to meet certain requirements before you can proceed with the rest of your calculation. The two main factors that you have to consider are choosing an inverter that can meet your continuous load demand. In other words, one large enough to handle the situation where all of your AC loads were on at the same time. And then also an inverter that can surge enough to start your heaviest starting load. The consideration there might be, what if all of your loads but your worst surging load were on, and then that load turned on as well? Surging loads might be, for example, refrigerators with compressors, or large motors, power tools, and so on. An AC load that surges might draw 5 to 6 times its continuous load demand for a few seconds or less as a surge. So the inverter must not only be able to operate these loads continuously, but supply enough surge current to meet the surge requirement of all your loads put together. Once you've chosen an inverter that meets those two requirements, now you have some more information that you needed to proceed. You have the efficiency of the inverter, and you have the input DC voltage of the inverter. With those values, you can proceed with the rest of your calculation. One helpful tool in estimating the surge of a large number of AC loads put together is a chart that we've assembled for you. In a simple system where you've got a few identifiable AC loads, you can simply add up the surge of those individual loads. But what if you're doing something complicated like a village, or maybe even just a large AC home where there's a large magnitude of small, medium, and large loads? You're not going to add up each one and try and mathematically figure that out. So you might use a tool like this, where we measure the estimated power requirement in watts or kilowatts on vertical scale, and your total average daily load in kilowatt hours on the horizontal axis. You'd find your estimation for your total load in kilowatt hours, and then read up to get a rough statistical estimation of the continuous range and the surge range that you'd need to meet those loads. What if our average daily load, our 24-hour load demand was, let's say, about 20 kilowatt hours a day, which happens to be pretty close to the average energy demand of typical American type of home. If we read up from 20 kilowatt hours a day into our continuous range, you see that you need an inverter that's roughly between, let's say, 4 and 6 kilowatts, continuous output rating, and a surge rating of anywhere from between 10 and 20 kilowatts. So with those numbers in mind, we can search through literature and choose an inverter that gives us the continuous rating and the surge rating that we need in order to operate all of those loads in an unpredictable sort of statistical way. Again, once you've chosen the inverter, now from the manufacturer specifications, you have the input DC voltage that inverter needed, 12, 24 volts, 48 volts, and you can estimate its average efficiency. And that's what we're going to need to continue our calculation. What do we mean by inverter efficiency? Well, efficiency in general is a measure of output over input. How much you get out versus how much you had to put in. With an inverter, we're dealing with electrical power out, AC, compared to electrical power in, DC. And we want to compare how well the device converted those two. Graphically, we can look at AC power coming out of an inverter and DC power going in. The efficiency is a measure of that AC power out divided by the DC power in. What we're going to use the efficiency number for is to calculate the DC power we have to put in order to get the AC power out that we've already calculated. Remember, the AC power out is your load demand that you've just added up. What you don't know is the number of modules you need to give you the amount of DC energy so that it can be converted into AC. So, by changing the formula a little bit, we get the DC power in is equal to the AC power out divided by the efficiency of the inverter. So obviously, we want that efficiency value to be as close to 100% as possible, so that we don't lose a lot of energy just in heat and noise, vibrations in the inverter itself. You typically read these off of manufacturer's literature. You could measure it yourself if you wanted to. Once we know the input voltage to the inverter and the average value of efficiency for that inverter, we can proceed with the rest of our AC load calculation. Because what we got to do is convert AC watt hours into DC watt hours. The way we do this is we take our AC subtotal and we divide it by the inverter efficiency and the input DC voltage to that inverter. And what are we doing in that calculation? First step, by dividing by efficiency, we're doing what we just talked about. We're converting AC power out into the DC power in. Or, conversely, the AC watt hours out, we're converting into DC watt hours in. And then by dividing by the DC input voltage, we're converting DC watt hours into DC amp hours. So by combining these two factors together, we can convert from an AC subtotal into amp hours for our AC loads. Now, finally, if you had AC loads and DC loads, you would add those two subtotals together to get a total bucket of amp hours per day that the solar array needs to supply. We can look at graphically this idea of a load that's the same every day, and this idea of a load that occurs only a couple days of the week and then stretching out the array, recharging over all 7 days of the week. Let's compare the two and you'll see the difference that we get. In the first case, we can look at a load that's fairly constant every day. So in that case, we'll size the array to give, on the average, the same amount of energy that the load needs every day. So the load demand and the array output are balanced. In this case, the array replaces the load every single day, and the battery is recharged on the average every day. So that's a typical situation. A lot of your calculations are going to be that simple. If you don't know exactly the load profile, you might simply guess that the load is the same every day, just to be safe. But if you know for sure that your load demand is only a few days of the week, like a weekend cabin, then you can economize on your array sizing. Why not do that? Why not save some money? So let's take a look at what the profile might be if you only had 2 days of load and 7 days in a week to recharge it. Graphically, we can show the load operating for 2 days. Starting from a full battery, by the end of 2 days, we're down in terms of battery state of charge. Why? Because the array isn't big enough. The array is sized to give enough energy in 7 days to replace what I've used up in 2. So on the actual days of operation, well, my batteries get dipped into a little bit, and they're left at the end of the weekend slightly discharged. And then during the other days of the week when the loads aren't operating, the array operates just like it's supposed to and gradually brings my battery bank back up to 100% so that I can have another weekend's worth of operation. So in this case, we're deliberately sizing the array too small so that it doesn't meet the daily load demand, but it meets the load demand over a period of a week. We've created for you a separate sizing form that can handle those kinds of scenarios as well. In doing the mathematical calculations, adding up your load demand, the hours per day, totaling it up, you shouldn't just blindly do that calculation. You should look carefully at each one of the loads and say, is there any way that I can make this load demand less? That's going to require fewer modules, fewer batteries, lower cost. You don't want to take away from the customer what they actually want, like lighting or refrigeration or appliance use. But there's a lot of loads that can be substituted that would give you much more efficient operation. For example, with lighting. Good example. Typical incandescent light bulbs are basically just heaters that put out a little bit of light. We can substitute most all incandescent lighting with modern-day compact fluorescent lighting. Example is this ashram bulb. These small compact lights, or what are often called PL lights, for parallel length, allow lighting to emit from a bulb with 4 to 5 times less energy consumption. So you get the same thing that you really wanted, which was lighting, but the energy consumption is 4 to 5 times less. So the number of modules, the number of batteries, 4 to 5 times less. These types of efficient lights are available both as individual bulbs or with ballasts that they can plug into for AC operation. If we have a DC home, you can combine those efficient lights with a DC type of ballast that operates from our DC power from our batteries, from our solar modules, and outputs high-frequency alternating current into the lamp. If you have an AC type of situation, then you can buy a plug-in type of ballast, plug the lamp in, and simply plug it into your standard AC lamps and operate the bulb from AC power. There's a wide variety of different types, individual lights, circular type lights, and even lamps built in with integrated reflectors that give more intense light. The point is that all of these lighting substitutions that you can make don't diminish the quality of life or the quality of load delivery, but they greatly diminish the number of modules, the number of batteries that you're going to need. Make your systems a lot more cost effective. We can look at other types of load efficiencies as well. We'll talk about those in a little minute. Further elaborating on lighting, though, is real important because it's one of the major loads that we use in photovoltaics. Remote cabin lighting, hospital lighting, lighting for schools, so on and so forth. Street lighting, the list goes on. So let's take a moment and really exercise that idea of how can we get more out of our lights. We can compare different types of light technologies, and we can see that there really are some differences in the choices you make. There are some trade-offs as well. The standard old incandescent light bulb that we're perhaps used to using is very poor in terms of output. The measure of output that we care about with lighting is lumens. Lumens per watt is the factor that we care about. Instead of looking at efficiency, which would be watts out versus electrical watts in, we only look at visible light emitted. And that's where the term lumens comes in. Lumens is a measure of visible light out. So if we look at lumens per watt, that's a measure of visible light output compared to electrical power input. We can compare the efficacy, or the lumens per watt, of different types of light. Standard old incandescent light bulbs only operate at about 15 lumens per watt, whereas these fluorescent lights operate at about 60 or 70 lumens per watt, an increased factor of 4 to 5. There's other lights that are even better. High-pressure sodium or low-pressure sodium lights operate at 100 or 150 lumens per watt. You have to be careful, though, and look at the light quality that you get from different lights. For example, the most efficacious of these lights, the low-pressure sodium lamp, is a light that you might have seen that delivers sort of an orangish glow. It's good for outdoor lighting, street lighting, and so on, but not good for indoor lighting or reading and so on. It would only be appropriate for certain outdoor applications. High-pressure sodium lights give a more white light, but it's still a strong, harsh light. But compare the efficiency or the efficacy of that light compared to standard old incandescent lights, and it's well worth it. But the clear comparison that we have to draw all the time in terms of indoor lighting is comparing fluorescent lighting to incandescent lighting. That's a changeover that you can always do. You'll still get good quality of light, and the amount of energy that you need is maybe 4 to 5 times less. So again, the number of modules and batteries you need are going to be less. Another important factor that you want to consider is the life of your lamps. We're looking at the initial cost of photovoltaic systems being kind of high. How can we make the cost over time as low as possible? Well, one way we can do that is with these compact fluorescent lights. The lifetime that we expect from them is quite long compared to the lifetime you get from standard incandescent bulbs. Standard value for an incandescent bulb might be as much as 1,000 hours, 800, 1,000, 1,200, something like that. 1,000 hours of operation before it has to be replaced. With a fluorescent light, we might get as much as 6, 7, 8,000, maybe as many as 10,000 hours of operation from that lamp before it has to be replaced. So not only does a fluorescent lamp use less energy when it's operating, but it operates for a much longer period of time. You put those two factors together, and that's a very powerful economic reason for buying what perhaps might be a more expensive light to begin with. It's really interesting to go through the process of comparing the purchasing of a more efficient load when you're designing your system and present that as a solution to a client who might already have an inefficient load that he's already paid for. The argument is this. You're proposing a solution of modules and batteries, perhaps inverters and so on, to a client. You also should present to them the fact that, hey, if you actually spent the money to purchase a more efficient or efficacious load and spent that money, you'd spend so much less money on the modules and batteries that the overall result would be cost savings. It's really interesting to carry this exercise all the way through. So by way of summary, when we're dealing with estimating our load demand, you should look very carefully at the actual numbers, the actual hours of operation that each load might be using, and also look very carefully at what each load might require, and is there any way to make those load demands more efficient. In the process of doing your load estimation, don't just do it once. Hardly ever is ever completed just one time. You always have to question your load information. Your accuracy in your load calculations won't make up for incorrect information that you got with or you started with in the first place. So take some time, if you can, to question both your calculations and the information that you got in the first place to see if maybe there's some way to economize. Some of the things you should take into account: have you anticipated future growth? Is there an indication that perhaps the loads that you're sizing today are going to be used for more hours, or more loads are going to be added in the near future? If so, that should be in the back of your mind and perhaps influence some of your rounding or some of your further decisions down the line. Is your load profile well known, or are you just guessing at it? Do you know if the load is used every day? Do you know how many hours it's operating? If someone tells you that the load is 10 amps, and you ask how many hours a day, they go, well, I don't know, I guess 24 hours. You should question that. An example might be something like a strobe light that's a lighting beacon. Yes, maybe it's operating in general over 24 hours, but the actual period of time that the load is operating is only a few fractions of a second per few seconds. You have to look very carefully at exactly how are the loads being used. Have all the loads been included? Have you really taken into account all of the loads that might be operating? And have you taken into account the quiescent loads that might be in some loads that have both a high level and a low level of load demand? An interesting thing to consider is your client a new user of electricity? Because in that case, once given reliable electric power from your photovoltaic generators, don't believe that they're only going to operate their lights or their appliances for a few hours. Once they get excited about having electricity, you can anticipate that there'll be future load demand growth. So if you question not only the mathematical process that you go through and make sure you don't make any errors in your math, but if you also question the process behind the load numbers, really question them, look at them carefully and see if there's any way to economize or improve on the efficiency of your loads themselves, I think you'll end up with not only a more cost-effective solution, but a more satisfactory solution for the client as well.